All right, we're going to get started today with a review exercise. But before you turn in your review exercise booklets, I want to teach you a little something that I think you learned about last year. Go ahead and not stop worrying about that for now there, Joshua. You can focus on it later. Just set it aside and don't worry about it right now. I'm going to talk about home ownership, right? Because one day, hopefully, you all will get married and have a family and have a house to live in. Maybe you'll rent. I rented an apartment for 3 years before I finally bought a house. We're not turning yet, Joshua, which is what I said a moment ago while you were fighting with that thing that was stuck. But hopefully one day you'll have a house. I want to just talk a little bit about how this works. Most people don't have tens or even hundreds of thousands of dollars sitting around wherewith to buy houses. Okay, so most people go to the bank and ask the bank to let them have the money to buy the house, right? So most people do it. You find it's called a finance company. It may be something like Rocket Mortgage. You've seen their commercials on TV, okay, all over the place on TV. Banks, credit unions will loan out money so you can buy a house. But technically, you don't own the house. The bank owns the house. You just get to live there. And you pay the bank back, usually for 30 years. You keep paying the bank until finally you own the home. Now, most people don't actually stay in one house for 30 years. Most people would stay in a house maybe, let's just say, 10 years, and they realize, oh, we need something bigger, or we want to do something different. So they'll sell the house, and when they sell the house, they get a bunch of money, and whatever they still owe the bank, they give the bank that much money. Does that kind of make sense how that works? So bank actually technically owns the home, and you just keep paying them to live there. Well, there's several things you have to pay for when you're buying a home. First of all, you have to pay the bank back the money that you borrowed, right? That's called the mortgage payment. Okay, it's spelled mortgage, but we don't usually pronounce the T very strongly. Mortgage. Say that with me, class? Mortgage. That's the payment that you make to the bank to live in the house. But banks aren't just interested in helping people live in houses. They're interested in making money. And how would a bank make money off of this? Well, you know this, class. Interest, right? So in addition to the mortgage, you also have to pay interest. And that depends on whatever your interest rate happens to be when you buy the house. When my wife and I purchased our home 7 years ago, we bought it at a 4% interest rate, which was really good back then. We're about to refinance at 2.75% interest. We're going to save about $100 a month this way. So interest. Hopefully right now interest rates are historic low. They may go even lower. They'll probably start going back up here soon, which is why we wanted to refinance now. I just have a stack of paperwork this thick I have to sign off on, all different stuff before we can actually get the process rolling. And I'm a busy man, so it's been sitting on the top of the piano for 2 weeks now, and I haven't gotten around to signing it yet. Anyway, but interest, okay? Interest is the money the bank makes off of you for letting you buy a house through them. But then here's the deal. What if that house were to burn down? Then the bank would be out a whole lot of money. And the bank doesn't want to be out a whole lot of money. So what do you do to protect the bank, really? We say protect yourself and your property, but really protect the bank from taking a huge loss. Insurance, right? And so there's insurance that you are required to buy as long as the bank owns the home. Now, frankly, even if you bought your own home outright, you'd want to get insurance on your house because heaven forbid, fire burns up your house and you lose everything. Okay, so theoretically, if my house burned down, insurance company would pay me, I think it's $120,000 to replace everything in my house. My house and everything in it aren't worth $120,000, but that's how much the insurance company is going to pay. Okay, so insurance, usually you insure for a whole lot. Typically, insurance is somewhere in the neighborhood of $1,000 to $2,000 a year for your insurance. Which, you think about it, then you could live in the house 60 years before you would be out the money. They gamble though on a lot of people's houses not burning down. Okay, and there's other things it covers: hail damage if you need to get your roof replaced, or vandalism, potentially certain things there. We'll talk more about the insurance side of things later, but you got to pay for insurance. That protects the bank. And there's one more thing. Uncle Sam looks at this and like, hey, how do I get a piece of the pie? I'm talking, of course, about taxes. Yes, to live in that house, you have to pay something called property tax. And all of this you pay every single month. A little bit on the mortgage, a whole lot on the interest, at least up front. Now, over time, you pay less and less interest and more mortgage. But initially, they rig the payment to where you pay a whole lot of interest up front because they want their money. And then a little bit of mortgage, insurance, and tax. Now, these two together are called escrow. Say that term with me, class. Escrow, okay? Escrow is an amount of money that is set aside to cover those incidentals, the taxes and the insurance. And what you'll do is you'll pay the bank every month all of this. And then it's usually once or twice a year, the bank will take care of sending the government your taxes. They'll take care of sending the insurance company the insurance premiums. You just pay escrow, you pay the bank all of this, and they'll take care of these other little things along the way. Does that make sense? Okay, so you're not writing one check to the government, one check to the insurance company, and one check to the bank. You pay it all to the bank, and they'll take care of this escrow amount. Okay, and again, that includes the insurance and the tax. Now, we're going to talk a lot about insurance later. For today, I just want you to know that it exists, that you have to pay for insurance. I want you to know you have to pay tax. Interest we've talked about. Simple interest formula, I equals PRT. It's not quite that simple in a lot of cases, but it's not too far off. And then the mortgage, well, you understand you have to pay for what you buy. It's kind of like buying on time, making little payments along the way. If you will, turn in your textbooks to page 18, or not in your textbooks, in your review exercise booklets to page 18. We're going to look at review exercise 20 at the top of page 18. And in review exercise 20, it says, when a person purchases a home, he's usually required to buy homeowner's insurance. In this way, the bank or lender is protected from loss in event of a disaster. There's another term I forgot to point out. Premiums are usually paid with the mortgage payment with taxes in escrow payments. So premiums are what you pay for insurance. And that's a term we're going to see a lot of because we're going to talk a lot about insurance. But a payment for insurance is called a premium. So the insurance premium, the property taxes, that's called escrow. You've got three problems that build on this idea. I want you to solve these three problems. They're on exercise 20. Go ahead and get started. let's go and take a look at these together. And Scott was first. It says, Mike and Samantha Smith bought a house. Last month, they paid the bank $231.47 towards the loan, $176.32 toward the interest, $75.12 for insurance, and $58.50 for property taxes. What was their total mortgage payment last month?
$541.41.
Good, $541.41. Is that what we had? Okay, next one. What was the escrow payment last month? Again, that's going to be a part of this mortgage payment, but what was the escrow portion?
$133.62.
Good, $133.62. Did we have that answer? All right, good. Just adding the insurance and the taxes together. Then it says if the insurance payment is the same every month, how much do Mr. and Mrs. Smith pay for homeowners insurance each year? Oh, you didn't do it right? Okay. Josh, you were next. You got the first two. Did you get the last one? What'd you get?
$675.03.
That is not correct, Lana.
$901.44.
There we go. $901.44 is correct. Short toss, sorry. We're simply going to take the, notice it says in the blurb in number 1, $75.12 for insurance, right? That's every month. But there's 12 months in a year, so you multiply by 12. And I think you might have multiplied by 10, Joshua.
I just added the 541 and the 133.
Oh, okay. No. Every month, it's $133.62 of escrow, but some of that's property taxes. So yeah, take the insurance times 12 for the monthly, and that would give you the yearly homeowner's insurance. All right?
What did you say?
It was $901.44. $901.44. All right. Any questions there? All right. We're going to talk a little bit more about insurance itself later on. For now, let me go and collect those from you. And turn your books to page 374. 374. And we'll take a look at the homework that you did as we've been talking about probability. I want to kind of review over what we were doing yesterday. And I mentioned this, I think it was to Josh yesterday afternoon. I realized there's a better way I could have explained a couple of the things at the end of the lesson. So we're going to kind of go back and redeem a little bit of the end of last lesson and to try to make it make a little bit more sense to you. And we'll do some extra practice today as well. So we're not going to go on to anything new today. Just practice what we've already been doing, mainly yesterday's material. Because first day material, y'all pretty much had it. Yesterday's lesson, need a little bit of extra work, and that's okay. We'll slow it down and make sure we understand this really well. But page 374 to 375, you got to skip number 14, but otherwise did the rest of those problems.
Because I didn't know how to do something.
Okay, all right. Well, we'll go over it. Hopefully you'll know how to do it moving forward. All right, excellent. All right, let's go and take a look at these together. Number 1, a spinner has 4 areas, numbered 1 through 4. The spinner will be spun twice. How many different outcomes could you get? For instance, you could spin a 1 and then you could spin another 1. You could spin a 1 and then a 2. You could spin a 1 and then a 3. You could spin a 1 and then a 4. You could spin a 2 and then a 1, then a 2 and then you get the idea? How many different outcomes are there? Scott? Oh.
I got 16.
16. The first spin, there are 4 different things you could get. The next time you spin, there are 4 more things. And remember the counting principle we said yesterday, we're going to multiply, not add them, to get 16 different ways you could spin back-to-back spins. 4 for each, but multiply 16 because of the 2 spins. For redemption, let's come back to you. Jason will watch 1 baseball game in each of the 3 states he'll be visiting. When he visits California, he could watch the Angels, the Dodgers, or the Padres. When he gets to Texas, and they left out, by the way, the Giants, San Francisco Giants are there. But anyway, in Texas, he could watch the Astros or the Rangers. And in New York, he could watch the Yankees or the Mets. How many different ways could he put together his baseball watching tour as he visits these 3 states?
36.
Oh, Joshua?
That's what I got.
All right, so he's visiting how many different states, class?
3.
3. Okay, so he goes to California, and while he's in California, how many different teams can he watch?
7.
In California?
No,
3.
I mean...
There are 3 teams in California. Then he's going to go to Texas. How many different teams in Texas can he watch? 2. Then he's going to go to New York. How many different teams can he watch in New York?
2.
2. He's going to make 3 different choices. Once he's going to choose between 3 things, then he's going to choose between 2 things, then he's going to choose between 2 more things. How many different ways could he make his baseball adventure work? 12 different ways. Does that make sense?
I have nothing
Right, and you took the 3 states, but each of the states is the choice in itself. It's not a choice of which state, and then what game, and then what game, and then what game is, while I'm in this, what game? While I'm here, what game? Does that make sense? So the states are not choices. He's already going to those states. It's which games will he watch while he's in those states. Make sense now? All right, let's take a look at the third one. Jesse's restoring his grandfather's 1945 sedan. He found 2 kinds of hubcaps, 2 different fabrics for seats, and 4 colors of paint. How many different ways could he restore the sedan? Third try's the charm here. What do you got? 16 is correct. But we'll take the 2 hubcaps times the 2 fabrics times the 4 colors of paint and get 16 different ways to customize the car. Number 4, Joshua. Myra is deciding on an outfit to wear to her cousin's wedding. She will wear either a red, blue, or green dress. There are also 4 possible shoe styles and 2 different options for purses. How many different ways could she coordinate her outfit?
24.
24. 3 dresses times 4 shoes times 2 purses would give us 24 different ways. Now, would they all necessarily match? We don't know, but it doesn't matter. We're going to go ahead and roll with that number. Number 5. Maybe she has new fashion sense. Maybe she's colorblind and doesn't know. I don't know. Anyway, number 5. Jeffrey is planning a class trip to Washington, D.C. His class can visit one of 2 museums, one of 3 national landmarks, and meet with one of 2 state senators. How many different ways could he plan the class trip? Lana?
3. One of each.
Right. He's going to do one of each of these, but again, he could go to either this museum or this museum. And after he does that, Lana, watching my hands, he goes to either museum. And then once he does that, if he goes to this museum, there's 3 different places he could go. Or if he goes to this museum, there's those same 3 places he could go. Well, so far, that's already 6 ways. So we're going to take the 2 museums. That's one choice he has to make. Then there are 3 national landmarks. That's another choice he has to make. Then there's 2 senators to meet with. That's another choice he has to make and they have to agree with. Minor detail. So really, we should say he could arrange this 12 different ways. Does that make sense? There's 3 things he's going to do on the trip, but there's 12 ways in which he could do those 3 things. Make sense? All right, number 6. Gloria is planning a flight from Miami to Seattle. She'll use one of 3 possible airlines. And for each of the 3 airlines, her flight will have a layover in either Houston or Denver. I've never flown to either of those cities, so I don't really know or care which one she goes to. How many different flight plans could she put together here? Joshua?
18.
18. Okay, so there's choice number 1 is what? What's the first choice?
Miami to Seattle.
She's already going from Miami to Seattle, okay? So she's going to make that trip. That's already predetermined. But she's got to choose. Which of these airlines am I going to fly? Is it going to be Delta? Is it going to be United? Is it going to be American, for instance? Okay? So there's how many airlines?
3.
She's got to choose one of those. So there's the first choices. There's 3 airlines to pick from. Then she's got to pick for each of these. She could have a layover in one of 2 places, right? She could either be stuck in Houston or stuck in Denver for a while. So that's how many more choices?
2.
2 more options for that second choice. So there's only how many different flight patterns? 6. 6 different flight patterns. Does that make sense? Yeah, remember, not adding, multiplying. The counting principle says we multiply. Now, we could have done what the book said and made a tree diagram and a list and all of that. I don't like all that. I'd rather multiply. But you have to be able to identify the choices. Does that make sense? The key to using the counting principle, and that's what we're going to practice more of today, is practice helping you see what are the choices I'm making, things of that nature. Number 7. Going back to problem number 1, what's the probability of spinning an even number for both spins? Well, let's think about it. The first spin, there's 4 numbers on there, right? How many of them are even, class?
2.
So if she only spins it once, and it spins around, what's the probability it lands on an even?
1 to 2.
2 to 4 or 1 to 2. There's a 1 to 2 probability of even, right? Then she comes around, she's like, okay, I'm going to spin it again. I say she. I don't think there's even a she in the problem. The person spinning is like, okay, I'm going to spin it again. What's the probability you get even the next time?
1 to 2.
And to figure out what the probability is that they both wind up even, we're simply going to multiply. And that's going to give us
1 to 4.
1 to 4. Now, This is not the way I showed yesterday. Yesterday I said this might be a good opportunity for us to use the old tree diagram, right? So she could spin a 1, a 2, a 3, or a 4 on the first spin, right? And then on the second spin, it could be a 1, 2, 3, or 4. 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 Now, how many of these show both spins? We already know that there are 16 possible ways this could work out. We already said that in number 1. Well, if she spins a 1 on the first one, you know she ain't getting 2 evens now. She's got to get an even on both of them. And a 3 on the first one already means no chance of even on both. But if she starts with an even but then spins odd, that's not even on both. And same here. So there are 1, 2, 3, 4 different ways out of 16 total that she could spin even on both. And this is the way I showed it yesterday. But it's quicker to say this. Chance of even, 1 to 2. Chance of even on the next one, 1 to 2, technically 2 out of 4, right? So what's the chances of even on both of them? Just multiply the possibilities together. Now, I'm assuming we probably did not get that answer on 7, but does it make sense now?
I still got 1 to 4.
You did figure out 1 to 4. Okay, great job. Anyone else get 1 to 4? All right, does it make sense now how we could have gotten it? What if I said, what's the probability she spins a 3 on the first and a 1 on the second? Well, what's the chances of a 3? 1 to 4. One number out of 4 on the spinner, right? Then what's the chances she turns around and spins a 1 on the next one? 1 to 4. So what are the odds that in order she goes 3, then 1? 1 to 16. You multiply. 1 to 4 times 1 to 4 gives 1 to 16. And think of it this way. There's 16 possibilities, right? But to start with a 3 and then a 1 is just one of 16 possibilities. So tree diagram makes it obvious, or you can use the counting principle and multiply those probabilities together. Does that make sense now? Even if it didn't make sense last night, does it make sense now? Let's look at the second number. Now this one is where it gets even more dicey. This is the one that I would have liked to have the idea, and I didn't formulate my thoughts as well as I should have yesterday. For problem 1, what's the probability of spinning an even number on at least one of the spins? Well, a couple ways in which you could look at it. Again, we could look at it this way. At least here's an even, at least here's an even, and all of these, they already had the even earlier, right? Here's an even, at least all of these started with an even. So that gives us 2, 6, 8, 12. There are 12 out of 16 ways to get at least one even. Do we see that? 12 out of 16 ways gets at least one even, or we could reduce that down to 3 to 4. Here's the way I think of it though. What if we wanted at least an even on one of the spins? One way to think of this would be if you want at least one of something. Are you listening? Not looking at your books. If you want at least one of something, let's look at it from the complementary point of view. Let's assume we don't want any evens. See that? Well, if we don't want any evens at all, on the first spin of the 4, how many are not even, class? 2. We need both of those possibilities. We reject the evens, we're saying no. Then on the next spin, how many evens are there? 2, but we don't want even, we want odd, so if we don't want even, how many not evens are there? Well, again, 2. So probability of not any evens at all, we can multiply the 2 nots together to get
4 to 16.
And if there's a 4 to 16 chance of it not happening, remember, total possibilities have to add up to 1. Then 1 minus 4/16 equals 12/16, or 3/4. If there's a 4 to 16 chance that you won't spin an even, there must be a 12 to 16 chance that you do. And that's a principle we're going to look at extensively here in just a few minutes. Go and look across the page. Number 9. A bag contains 4 yellow marbles and 1 blue marble. Kyla will draw a marble 4 times, replacing the marble after each draw. What's the probability of getting the blue marble all 4 times? Well, how many desired outcomes do we have, class? 1. We have 1 desired outcome, and that is blue, 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 blue. Correct? We want blue each of the 4 times. All right? How many total possibilities are there? Well, the first time she reaches in the bag, there are how many marbles, class?
4.
Careful. 5. Read again. A bag contains 4 yellow marbles and 1 blue marble. So how many marbles are in the bag, class? 5. So the first time she reaches in, how many are there? 5. The next time she reaches in, assuming she put it back, how many marbles are there?
5.
And the next time? And the next time? So how many total ways could she pull marbles out of the bag then? On 4 tries, where there are 5 marbles each time. 625 total ways she could draw marbles out. She could do blue, 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 green and screw it up at the end. She could screw it up on the very first one and draw yellow, and then, whatever she draws after that. There are 625 different ways she could draw marbles out of that bag. But the only way she wants is blue 4 times in a row, which is a tall ask. It's so tall, it's 1 to 625. Now there's another way to look at this. Look at each draw individually. You with me? The first time she reaches in the bag, how many marbles are in there, class? 5. How many of them are blue?
1.
So if she just makes 1 draw, what's the probability of blue? 1 to 5. She puts it back, stirs them around, pulls that again. What's the probability of blue?
1
Same thing again is obviously again going to be 1 to 5, and then the last one's going to be 1 to 5. We could multiply all of those together, and it would equal 1 to 625.
I just got 1 to 5.
Well, each one is 1 to 5. Each time she draws is 1 to 5, but she wants, literally, Lana, it's a 1 to 5 chance she just does that the first time. That's not great odds, right? But the odds of pulling blue and then blue again, that makes the chances that much lower. Now it's 1 to 25. And then she tries to do it again. Now she's 1 out of 125 chance of that happening. And finally, on the 4th draw, now we're up to 1 out of 625 chance of blue, then blue again, then blue again, then blue again, when there's only that 1 blue marble each time out of 5. We multiply the possibilities. Are you seeing that? Okay, let's take a look at number 10. A buffet has 6 beverages, 12 entrees, and 3 sides. Kelsey selected 1 of each and returned a receipt. What's the probability that Kelsey selected the same 3 options as her sister, Mackenzie? Now, this does not account for the fact that sisters oftentimes like similar things or like exact opposite things. If we didn't know anything about Kelsey, we didn't know anything about Mackenzie, we're strictly looking at the mathematical possibilities. Well, how many possibilities are there, class? There's 6 beverages, 12 entrees, 3 sides. How many different things, ways could we put these items together? 216 different ways we could put them together, right? But the only one way we're interested out of 216, that's 6 beverages times 12 entrees times 3 sides. The only way we're interested in is she picks the one exact same combination as her sister. So what's the probability she picks exactly what Mackenzie did?
1 to 7.
Wait.
1 out of 216.
Oh.
She picks one particular arrangement of 3 things. And that one arrangement is 1 out of 216 different ways she could have picked. Another way is this. What are the odds, class, she picks the same beverage? There's 6 of them, so 1 to 6. What are the odds she picks the same entree? What are the odds she picks the same side?
1 to 3.
And when you multiply them all together, 1 to 216. Does that make sense? So picking the same beverage isn't that tall of an ask. 1 to 6 aren't terrible odds. Picking the same entree is a lot lower odds. But picking both of them the same makes the odds that much lower. Do we see that? You multiply the probabilities of each together to get total probability. We're going to work on that again in just a little bit. Looking at the rest of the homework. Number 11. You're just simplifying expression. And what did you get for your answer on number 11, Joshua?
2 times 9 times n squared times O times p cubed.
Now, what is 2 times 9? Because we don't like to leave numbers unsimplified.
Oh, yeah, 18.
And then let's not use the times. Let's just run it all together. What's the best way to simplify that expression? So what do we get for our answer, Joshua?
Answer.
What was your answer on number 11 when you simplified?
2,
No, what should have been your answer, Joshua, on number 11?
18 times.
No, not times.
Parentheses.
No, not even parentheses. Mush it together. Help him, Lonnie. He's not understanding.
18 n squared O p cubed.
18 n squared O p cubed. Run it together. All right, so Joshua, for redemption. Number 12, what should we have gotten for our answer?
12d e e to the 4th power f squared.
There we go. 12 de to the 4th f squared is correct. And what about number 13? Scott?
6r to the 5th t cubed.
Good. 6r to the 5th st cubed. A little algebra review there. Hadn't seen that in a little while. And just kind of mixing it up there. Number 15, go ahead and read that for us if you would, Lana.
During the Russian chocolate company printed rewards for a year's supply of chocolate on 100 actors. If they sold 4 million chocolate bars during the promotion, what is the probability that a randomly selected chocolate bar is a winner?
All right, this reminds me of Charlie and the Chocolate Factory. How many have read that book or seen the movie? There's the golden ticket inside the chocolate bar. Well, there were only 5 lucky winners. Here there's 100. And, but anyway, 100 lucky winners, but out of 4 million chocolate bars. So class, the event here is the probability of a winner, right? Probability of a winner here. How many winners are there going to be, class? 100. That is the outcome we desire, is to be a winner. And there are 100 winners going to be chosen. The sample size is how many total chocolate bars there are in the first place.
4 million.
4 million. But we always reduce the ratio, don't we? And the quickest way is to simply knock off 2 zeros to get a probability of 1 to 40,000. Do we get 1 out of 40,000? You knock off 2 zeros. There's 1, 2, 3, 4 zeros left, so 1 over 4, 1, 2, 3, 4 zeros. 1 to 40,000 is your probability of being a winner. In other words, statistically speaking, if you want to win, you would have to buy 40,000 chocolate bars to guarantee yourself a win. Technically, it doesn't guarantee you, but it really close does. All right, mathematically it should, though, you know, odds would have it the 40,000 first bar you didn't buy actually had it, and some kid comes along and buys 1 chocolate bar and wins, a la Willy Wonka, right? Not Willy Wonka, there was the little kid's name. Charlie. Yeah, duh, Charlie. Charlie Bucket. And so he buys the 1 chocolate bar. It happens to have the golden ticket. Actually, I think he bought 2. He bought 2 chocolate bars. The second one had the wrapper in. Anyway,
Yeah.
questions on this? Questions on this?
Wait,
Yes, ma'am.
on number 8,
Yes.
I thought like one of the spins would just be 1 to 2.
Well, either one of the spins is 1 to 2.
Oh.
Another way to look at it might be this. If he spins, let's say he's got a 1 to 2 chance of spinning the even number on the first spin, right? Well, let's say, class, look up this way. Let's say he gets the even number. Does it even matter what he spins on the next spin? No. The next one could be 4 to 4, right? We don't even care what he spins on the next one because he already got it, right? Or if he's going to get it on the second one, then all we care about is that he, then we're like, well, he's already got it, so who cares what he got on the first spin? So you could say then that it's a 4 to, actually that doesn't work out, that's 4 to 8, 9. 3 to 4. Yeah, no, my other way works. That way doesn't work. But yeah, there's a 3 to 4 chance he gets it on at least one of the 2 spins. All right, let's address that a little bit more. Go back to page 372. Go back to page 373, excuse me. Page 373. Let's look at number 11, because we worked it yesterday, and we worked it with that tree diagram. But again, I want to liberate you from tree diagrams. We don't like tree diagrams, right? Take a while? No fun? Okay, so I want to help you think mathy here. Go ahead and read number 11 again for us, and it's going to refer to a problem on a previous page. Scott?
From problem 2, what is the probability that John did not draw any reds on his 3 draws?
All right, so we're going to go back to problem number 2. Read problem 2 for us now, Lana.
There are 3 marbles in one bag. 1 red, 1 green, and 1 blue. John will randomly draw a marble 3 times, replacing it.
All right, so there's 3 different draws. Each time, there are 3 things in there. So there's 3 different draws. Now, it says, what's the probability he will not pick a red, correct? How many reds are in there?
1.
1. Out of how many?
3.
So there's a 1 to 3 chance he does get red, correct? But what are the odds he doesn't? 2 to 3. So on the first draw, there's a 2 to 3 chance of no red, correct? What about the second time? Assuming he puts whatever he drew out, what are the chances on the second draw there's no red? 2 to 3 again, right? Still 2 to 3. He puts that marble back in, he draws again. Now what are the odds of no red? 2 to 3 again. So what are the odds he actually doesn't wind up with a red on any of them? We multiply these together to get
8 over 20.
8 27s. Now that's interesting, because that's an 8 27s chance of not even 1 red. Question: what are the odds of 1 red at least? If there's an 8 to 27 chance he doesn't get any reds at all, then the odds of at least getting 1 red must be
1 to 27.
not getting a red, getting 1 red. These would be complementary, wouldn't they? The odds of not doing something, the odds of doing something are complementary. What do we know about complementary probability? You subtract from 1. So, if we subtract 8 27ths from 1, which would be 27 27ths, what are the odds he does get at least 1 red? 19 27ths. Which is more likely? That he draws 3 times and doesn't get a single red, or that he draws 3 times and does happen to get a red somewhere? That he does get a red somewhere is the probability. So that makes sense. 19 and 27 are much better odds. Do we see how we can use the not to get the what if? Let's take a look at the next one. Number 12. From problem 3. So we're looking at the Larson family. Okay, the Larson family, 3 kids. Remember the infant, the kindergarten, teenager. Each one, of course, is boy or girl. What is the probability all 3 kids are girls? All right. Well, what's the probability the first kid's a girl, class?
1 to 2.
1 to 2, because the first kid's either a boy or a girl, right? What's the probability the next kid is also another girl? 1 to 2. Now, so far, total, that's a 1 to 4 chance. But a 1 to 2, all right? What's the odds the next kid's a girl?
1 to 2.
1 to 2. So what are the odds that all 3, girl, 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 on a row, class?
1 to 8.
1 to 8 when we multiply. Does that make sense? All right. Look at number 13. Number 13. This makes me think a little bit of Yahtzee, except there's only 4 cubes, 4 dice. Okay? 4 6-sided cubes are rolled at the same time. What's the probability if 5 was rolled on all 4 number cubes? Okay, so in Yahtzee, you all know what, y'all ever played Yahtzee?
Yep.
Okay, except this is with 4 dice, and you only get 1 roll, okay? So you're like, well, let's just hope they're all 5s. Really low chances of that happening, right? Like, we just know that intuitively. It's probably not going to happen. Well, what's the odds that the first die is a 5, class?
1 to 6.
1 to 6. There's 6 sides on there. Only one of them is a 5. So there's 1 to 6 on the first one. What's the odds you get another 5 on the next die? What's the odds that the next die also has a 5? And the odds that the last die also has a 5? What are the odds then that all 4 dice all have 5s on them?
1 to 1,296.
You have a 1 out of 1,296 chance. In other words, mathematically speaking, if you were to roll the dice 1,296 times, one of those rolls should have been a 5, 5, 5, 5. Make sense? In other words, probably not going to happen. All right. Look at number 14. Number 14. Oh, here's an interesting thought, though. Stay with me. What are the odds you don't get any 5s. Ever played a game called Farkle?
Yes.
Okay, it's basically you need 1s and 5s or else you pretty much don't score, or really crazy special rules, right? They just happen on there, okay? But basically you need 1s and 5s. Well, what are the odds you don't get any 5s? Well, what's the odds on the first roll that first die ain't a 5?
4 to 6.
5 to 6.
Oh,
Because the other 5 numbers, 1, 2, 3, 4, 6, are not 5s, right? So there's 5 possibilities on the die that are not 5s. What's the odds the next one ain't a 5?
5 to 6.
5 to 6. What's the odds the next one's not a 5?
5 to 6.
And the odds the next one's not a 5.
5 to 6.
So what are the odds of no 5s at all?
625 over 1,296.
Impressive. 625 to 1,296 chance that you don't get any 5s at all when you roll those 4 dice. So let me ask you, if that's the odds of no 5s at all, what are the odds of at least 1 5? If that's the odds of not getting any 5s whatsoever, then the odds of at least having 1 5 must be...
Yeah, that's what I got.
671 to 1,296. Notice, slightly better odds of getting at least 1 5 compared to getting no 5s. Make sense? All right, let's take a look at page 378. Page 378. I want you to work numbers 21 and 22 in the review section. Page 378, numbers 21 and 22, they're in the review. Take about 3 or 4 minutes to work these problems. Anytime there's an at least 1, start by figuring the odds of not getting anything at all, and then subtract to get the odds of at least 1. Okay, so the best way to approach at least 1 is start by saying, well, what are the odds of not getting anything? Now subtract from 1 to get the odds of actually getting at least 1. Basically the same idea as a complement. The complement is 1 minus the probability of something. Probability of at least 1 of something has to equal 100% certitude minus the probability of none at all. Because the opposite of getting nothing is getting at least 1 thing, right? After class. All right, let's go and put the pencils down. Let's see how we did on these. The first problem should have been pretty straightforward. We've got a cube, a die, with the numbers 1 through 6 on it. What's the probability of rolling a 6? Josh?
1.
So you got a die, roll it around your hand, roll it on the table or on the floor, and it comes out. What's the odds it's a 6? Lana?
1 to 6.
1 to 6. There's 6 possible numbers. The odds of getting one of those, a 6, is 1 to 6. All right, what is the odds of getting a number that isn't 4? Scott?
5 to 6.
5 to 6, because there's 5 other numbers besides 4 you could get. What are the odds of an odd number, Joshua? 1 to 2. 3 odd numbers on there, 3 out of 6. What's the odds of getting a number that isn't a 9? Lana?
6 out of 6 or 1.
Okay, 6 out of 6 or 1. There aren't any 9s on there, so of course you're going to get something that's not 9. Let's see, come on, something that isn't 9, you know? Hey, yes, I did it! Anyway, what about a number less than 5, Scott?
2 and 3.
Good, there are 4 numbers that are less than 5, so 4 out of 6 would reduce to 2 to 3. What about a number that isn't less than 5? A number that isn't less than 5. Josh?
1 to 6.
I got 1 to 3.
1 to 3, because 5 isn't less than 5 and 6 isn't less than 5. So there's 2 numbers that aren't less than 5, so that's 2 out of 6 or 1 to 3. All right, now we change the situation. We've got a spinner that goes 3 ways, 1 through 3, and it's spun twice. What's the probability of getting a 3 on both spins? Start by thinking, what is the probability of a 3 on just the first spin, class? 1 to 3. What's the probability of a 3 on the second spin?
1 to 3.
So what's the probability of a 3 on both spins?
1 to 9.
1 to 9. Did we get that? You
I got
multiply the
7.
probabilities together. All right? What's the probability of getting a 3 on at least one of the spins? The best way to approach this is to say, well, let's start with the probability of no 1s at all. We don't want, no 3s at all. Well, what's the probability of no 3 on the first spin? 2 to 3. What's the probability of no 3s on the second spin?
2 to 3.
So what's the probability of no 3s at all?
4 to 9.
4 to 9. That's the probability of no 3s. So what's the probability that at least one is a 3? 5 to 9. Does that make sense now? You find the probability of it not happening at all and subtract from 1 to get the probability that at least one of those things happens. Does that make sense? All right, again, we're going to practice even more with this in our next lesson as well. Stay with me. You guys are dismissed, but shut the door behind you, please. What's the odds of getting an odd number on both spins? Well, how many odd numbers are there? 2. If the spinner goes 1 through 3, right, it's a 1, 2, or 3 spinner, then the odds of getting an odd number on the first spin are 2 to 3. What's the odds of an odd number on the next spin? 2 to 3 again. What are the odds that you go odd, then odd again? 4 to 9. You multiply the probabilities together. Starting to catch on to the pattern here? All right, and if not, that's okay. So we're still going to work on this a little bit in our next lesson. We are going to go ahead, but we're going to be going over this a little bit more. What about an odd number on at least one spin? Anytime it says at least one, class, we need to first find the probability of nothing. Okay, so what if we don't want an odd number? Well, the only even number on the spinner is 2, right? So one of the 3 numbers on the spinner ain't odd, right? So the odds of not odd would be 1 to 3. But then you spin it a second time. What are the odds that it's not odd again? 1 to 3. So what are the odds you don't get any odd numbers at all?
1 to 9.
1 to 9. So if that's the probability of not getting any odd numbers, then the probability that at least one of your spins is odd would be 8 to 9. You're almost guaranteed to get 1 minus 1/9 equals 8 ninths.
Oh.
Right.
Oh,
1 as in 9
yeah.
ninths minus 1/9 equals 8 ninths. We'll practice more with that idea in our next lesson. Homework for this evening is to read pages 375 to 377. Read 375 to 377. We're going to talk about permutations in our next lesson. Mind-blowing sounding. It's really not that bad. But I do need you to read pages 375 to 377 so you'll kind of a little bit know what's going on when we get there in our next lesson on Monday. The only written homework, very short for a change. Page 373, review 15 through 19. Page 373, the review 15 through 19. So just 5 short little problems. You're welcome. I do want you to read, though, and try to understand. You may not, but try to understand what you're reading. All right, you are dismissed. Have a wonderful rest of your day.